Good morning. This is the second lecture on centrifugal compressor. Contents of the lecture are the compressibility effect, the inlet Mach number, the diffuser system, the compressor characteristics, surge and choking. I'll initiate the discussion today with compressibility effect associated with a centrifugal compressor and how to control the inlet Mach number and thus the formation of shock that often appear at inlet of a centrifugal compressor. To illustrate the compressibility effect of a centrifugal compressor, the meridional section of the compressor is presented here, where I tip diameter and I root diameter have been indicated along with impeller radius and its width. So R2 be the impeller radius, outer radius, and B2 is the width of the impeller at exit. Thus, you can appreciate the impeller passage, that is the meridional flow through the impeller, as I'm indicating here. Furthermore, I have taken a section which is marked by AA, and the section has been plotted here, which is the plan view looking from the top. Thus, you can understand this is the inlet of the impeller, which is the I. And let us consider U1 be the blade speed at the inlet. Thus, if you consider the velocity triangle at inlet, we'll get U1 plus W1 is equal to C1, where W1 is the relative inlet velocity and C1 be the absolute velocity at inlet. Now the direction of W1 will decide the entry of flow to the impeller, and often a shock may form on the convex surface of the eye depending on the inlet Mach number, which would be decided by W1. The relative Mach number at inlet is very important. When you need to control the inlet relative Mach number, otherwise shock will appear, thickening the boundary layer. Often the boundary layer will be broken, enhancing losses. Thereby, we need to control or restrict the inlet relative Mach number so that the shock would not occur and there will be a smooth entry of flow as per the design criteria. Now the question is, how can we control the inlet Mach number or W1? To control the inlet relative velocity, often we provide a guide vane at inlet that produce a positive swelling component, that is some value of C theta 1 as I have indicated by the velocity triangle. Now considering the U1 blade speed be same, if you draw the velocity triangle with a positive inlet swirl C theta 1, you will realize that W1 has decreased. So I have considered now, which has been drawn by a form line U1 plus W1 by C1. This is the velocity triangle with a positive pressure at inlet, and the dotted triangle I have superimposed here, which is the triangle here that is without guide vane. Now you can appreciate that W1 has decreased. Thus, the relative inlet velocity can be controlled by providing a guide vane at inlet. What I have stated, I have summarized here, considering that I have written here for your understanding. At inlet, the air is deflected through a certain angle over the convex surface of the eye before it passes to the radial channel of the impeller. The air has a tendency to break away from the convex surface of the eye, where the Mach number is extremely important. A shock might occur, leading to undesirable increase of losses. Thereby, the inlet Mach number needs to be restricted as shown in the figure. Thus, the inlet Mach number is restricted to 0.8 so that no undesirable shock appears within the blade passage, breaking away the boundary layer from the surface as indicated in the figure. Let me now define the relative inlet Mach number as MR1 is equal to W1 divided by root over gamma RT1, where gamma RT1 is equal to sonic speed. Thus, please note that sonic speed depends on the local temperature. Hence, MR1 should lie within the limit 0.7 to 0.8 as stated earlier. Please note that the static temperature at exit is more than the inlet, and hence the local sonic speed. What I like to say here, the local sonic speed at exit will have a higher value than that of the inlet. That it is expected that by restricting the Mach number at inlet, the whole compressor passage would be safe from the formation of shock wave. Thus, the inlet is more critical than the exit section of the impeller. Furthermore, considering the uniform inlet flow C1, the relative velocity W1 is more at the tip of the eye of the impeller than that of the hub. Why it happens? Because the blade speed at tip will be higher than that of the hub, and thereby W1. Thus, the tip at inlet is considered to be critical. In brief, MR1 at the tip of the eye is critical, and it is kept always within a limit to avoid shock within the impeller passage. Another important point to be noted that the inlet relative Mach number MR1 increases with the eye tip diameter. Thus, the ratio of eye root to eye tip diameter is an important parameter, and it should be kept within the limit 0.4 to 0.65. Now I have discussed here how to control the inlet Mach number. Although I have indicated this, still let me elaborate here for your appreciation that often an inlet guide vane is provided which reduces W1, the relative inlet velocity, with an enhanced positive pressure. I have indicated that in this figure. I have drawn here the inlet velocity triangle at tip with a guide vane and without guide vane. The velocity triangle with guide vane has been indicated here with the far line, and without guide vane is shown by the dotted line. So U1 be the blade speed at the high tip, and W1 be the relative velocity. So vectorial addition of U1 plus W1 would be equal to C1. Now because of inlet guide vane, the C1 will be tilted at an angle alpha 1 with respect to the tangential direction, providing the additional swirling component which is indicated here by C theta 1. Now if you draw the velocity triangle with and without swirling component, that is with and without guide vane, you will appreciate here that W1 has substantially decreased because of guide vane that provides a positive swirling component or positive value of C theta 1. Thus, it has been appreciated that MR1 at tip has decreased. However, because of positive value of C theta 1, the work input per unit mass flow rate has also reduced. Thus, the Euler work, which is given by U2 C theta 2 minus U1 C theta 1 would decrease, reducing the pressure ratio. Hence, to maintain the same pressure ratio, the impeller diameter has to be increased. So what I have told over here, that in brief, by providing inlet guide vane, we can reduce or we can control inlet relative Mach number by providing an additional swirling component at inlet. However, it decreases the work input. Thereby, the pressure ratio of the compressor will decrease. Hence, to maintain the pressure ratio, we may have to increase the impeller diameter. I'll discuss now another important section, that is diffuser system, vane and vaneless diffuser, that is volute casing. Furthermore, I'll try to derive the analytical expression for the diffuser performance. I have discussed here about the diffuser system. Centrifugal compressor and pumps are in general fitted with either a vaneless or vane diffuser to transform the kinetic energy of fluid at impeller exit to the pressure energy. The volute casing is the final component of a centrifugal compressor or pump. This is a spiral-shaped channel of increasing cross-sectional area, and the sole purpose of a volute casing is to collect the fluid from the diffuser vane or from the exit of the impeller and to deliver the fluid to the exit port. I have discussed first with the vaneless diffuser. The vaneless diffuser is the volute casing, and I have indicated here the schematic of the volute casing with the impeller, where you can realize that cross-sectional area or the flow area in the volute casing is gradually decreased. Due to the dynamic action of the impeller, the kinetic energy of fluid at the exit of impeller will be increased, and then it will be diffused gradually in the volute casing due to increasing cross-sectional area. Now, I have considered here by a dotted line the meridional flow path of the fluid within the volute casing. So again, let me repeat, the dotted line is the meridional streamlines within the volute casing. At any point, say, let us consider P be the any point on the streamline, and C is the magnitude of velocity that I have obtained by drawing a tangent to the streamlines, which has been indicated by the dotted line. Now, this C has two components, that C is the absolute velocity, has two components which is indicated by C theta, that is tangential component, and CR being the radial component. The absolute velocity C makes an angle alpha with respect to the radial direction. Thus, the C is divided in two components. One is C theta and CR. C theta be the soaring component and CR be the radial component. Thus, the simplest concept of diffusion in a radial flow machines is one where the spiral velocity component C theta is reduced by an increase in radius, that is, considering the conservation of angular momentum, and further radial component is controlled by the radial flow area. Thus, let me repeat again what I wanted to mean here, that the concept of diffusions in the volute casing for a radial flow machine is that here the spiral component C theta is reduced by increasing the radius using the conservation of angular momentum, and the radial component is controlled by radial flow area. Now, if m dot be the mass flow rate, then within the volute casing, applying continuity equation, I can write m dot is equal to rho A into CR. CR is the radial component of velocity, and A is the flow area, where A can be written as twice pi r into B, where B is the width of the passage. Thus, from this equation, which is m dot is equal to rho into twice pi r B into CR, I can write R into CR approximately is a constant number, which has been indicated by CO1. Further, if we consider, or if we assume the flow is frictionless within the diffuser, then considering the conservation of angular momentum, it can be stated that R into C theta should be equal to constant. Thus, I can write tan alpha is equal to C theta by CR, which is also a constant as the fluid is diffused outward. Therefore, under the conservation of angular momentum and considering the flow is frictionless within the diffuser, I can say the flow maintains a constant inclination alpha to the radial line, and thus The flow path traces a logarithmic spiral. This explains why we use a volute casing for diffusion. The advantage of volute casing is that it is simple, less costly than vane diffuser, and it is used for a wide operating range. What is the disadvantages? Without vane diffuser or for a vaneless diffuser, with only volute casing, it becomes a little bit bulky. Therefore, the disadvantages are size and thus the weight. I have discussed here about vane diffuser. Here the vanes are used to remove source of fluid at a higher rate than is possible by simple increase in radius and thereby reducing the length of flow path and the diameter. Thus, the vane diffuser is clearly an advantage where small unit size is important. I have indicated here the schematic of a vane diffuser where I have indicated the impeller followed by the diffuser vane and then the volute casing. I have also illustrated the meridional flow within the blade passage in blade to blade plane where one can appreciate the non-uniform flow. Furthermore, there is a gap between the leading edge of the vane and the impeller exit, which has been indicated by vaneless space. This clearance is important for the diffusions of fluid. Thus, as indicated here, C2 be the absolute exit velocity of air from the impeller and C3 be the absolute velocity of air from the diffuser. So the air is first diffused in the diffuser and then in the volute casing. And here, as I have indicated, swirl of fluid is removed at a faster rate, and thus the size of the unit is relatively small. I have indicated here that clearance between the diffuser vane and the impeller is important, and this clearance is maintained of about 0.04 D2 for the pump, where D2 is the diameter of the impeller, where for a compressor it is recommended as 0.01 to 0.02 D2. Furthermore, the flow follows an approximately logarithmic spiral path in the vaneless space, and then the flow is constant by the diffuser channel. Following important points to be noted regarding the vane diffuser. The vaneless space allows the non-uniform flow within the impeller to mix out, where the absolute velocity and hence the Mach number is reduced. Thus the flow enters the diffuser vane with a less steep velocity profile. Even the supersonic flow at the impeller exit is decelerated in the vaneless space at constant angular momentum without shock. This is a great advantage. For rapid diffusion of flow, the axis of the channel is straight and tangential to the spiral path. The passages are designed on the basis of a simple diffuser channel theory with an equivalent angle of divergence in between 8 to 12 degrees to control the flow separation. Please note that higher angle of divergence leads to flow separation within the diffuser vane. Number of diffuser vanes can also have a direct bearing on the efficiency and surge margin of the compressor. Surge occurs at higher flow rate when the vane diffuser are used than when a simple vaneless diffuser design is adopted. Thus, it is better to have fewer diffuser vanes than impeller vanes. Roughly about 1/3 number of vanes are recommended in order to achieve a wide range of surge-free flow. Furthermore, the direction of exit velocity from the impeller C2 is dependent on mass flow rate and the blade speed. Thus, for a shockless NT, the vanes should be set at a proper angle. Performance may suffer from the effect of incidence, and hence, for a vane diffuser, the efficiency falls at a faster rate for the off-design condition than the vaneless diffuser. I have explained here the performance of a diffuser. The diffuser is an important element of a centrifugal compressor or a pump. Its purpose is to reduce the velocity of flow leaving the impeller, resulting in an increase in pressure. The diffuser performance can be simply depicted as a non-rotating channel where the flow area increases in the direction of flow as indicated in the figure. The figure represents the schematic of some diffuser geometries where I have considered the diffuser as 2D channel, or its section is considered as conical. Now in figure A, I have considered the diffuser as a 2D channel where the section 1 represents the inlet and section 2 indicates the exit of the diffuser, and W1 be the width at inlet, theta is the angle of divergence, and N be its length. Then area ratio can be projected as A2 by A1 is equal to 1 plus 2n divided by W1 into tan theta. For a conical section, the same area ratio would be A2 by A1 is equal to 1 plus n divided by R1 tan theta whole to the power square, where R1 be the radius at inlet, n is the length of the diffuser, and theta is the angle of divergence. Although the basic diffuser appears to be a simple geometric device, it is affected by two serious fluid mechanical problems. The primary problem is the tendency of boundary layer to separate from the diffuser wall if the local rate of diffusion is too rapid, resulting in flow mixing and large losses in a stagnation pressure. On the other hand, if the diffusion rate is too low, then the fluid is exposed to a long length of wall, and thus the fluid frictional loss increases again. Clearly, there must be an optimum rate of diffusion between two extreme cases, as stated earlier, where the losses would be minimal. The experiments conducted on both 2D and conical diffuser have indicated that an equivalent angle of divergence would be in between 8 to 12 degree, which will result in optimal recovery of pressure. The diffusion process can be represented on a Mollier diagram, that is on the HS diagram, by a change of state from point 1 to point 2 with the corresponding change in pressure from P1 to P2 and the change in velocity from C1 to C2. The Mollier diagram for a diffuser flow has been indicated here, where P1 is the pressure at inlet to the diffuser and C1 be the magnitude of velocity, and thus P2 be the exit pressure and C2 be the magnitude of velocity. Though I have drawn the P1 constant pressure line P1 and P2, and 1, 2 here is the diffusion process, which is non-isentropic. That is, entropy will increase during the process 1, 2. If I add C1 squared by 2 to H1, I'll get H01. So H01 must be equal to H02. Thereby, I have got P01 and P02 line. And if you draw a vertical line representing the isentropic process, you will get the point 2s and 0, 2, 2, 0, 2s. 0, 2s is the isentropic total temperature or total enthalpy at exit, and similarly static temperature or static enthalpy at exit is represented by H2s or T2s. Now I can define the diffuser efficiency. The diffuser efficiency eta D is defined as the ratio of isentropic change in enthalpy to the actual change in enthalpy in the process of diffusion, considering the steady and adiabatic flow in the stationary passage, that is within the diffuser. I can consider H01 must be equal to H02. Thus, H2 minus H1 must be equal to half into C1 square minus C2 square. So here I have presented the schematic of the diffuser, where C1 be the inlet velocity and C2 be the exit velocity. Furthermore, the equivalent reversible adiabatic process from the state point 1 to the state point 2s, that is, here it is, I can write H2s minus H1 must be equal to half within bracket C1 square minus C2s square. Hence, the diffuser efficiency eta D can be stated as H2s minus H1 divided by H2 minus H1. That is isentropic enthalpy rise divided by actual enthalpy rise. This can be stated as C1 square minus C2s square divided by C1 square minus C2 square. Furthermore, eta D can be expressed in terms of temperature as eta D is equal to T2s divided by T1 minus 1 over T2 by T1 minus 1. It is noted that The total pressure recovery factor P02 by P01 can be used as a measure of diffuser performance. Thus, it may be more convenient to represent the diffuser efficiency in terms of pressure ratio as for the isentropic process 1 2s, I can write T2s by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. As referring to the HS diagram, I can say now for the constant temperature process 01, 02, we can write T into ds is equal to minus dP by rho, which can be combined with the ideal gas relation as P by rho is equal to RT, which yields ds is equal to R into dP by P. Upon integrating for the whole process 1 and 2, we get del S, that is change of entropy, is equal to R into ln P01 by P02. Again, for the constant pressure process 2S2, that means here 2S2, I can write T to ds is equal to dH is equal to Cp into dt. Therefore, again by integrating I can get del S is equal to Cp ln T2 divided by T2S. Equating these two relations and using R by Cp is equal to gamma minus 1 by gamma, we find that T2 by T2S is equal to P01 by P02 to the power gamma minus 1 by gamma. Thus, I have got an important relation that T2 divided by T2S is equal to P01 divided by P02 to the power gamma minus 1 by gamma. Now I can write T2 by T1 is equal to T2 by T2S into T2S by T1. Now T2 by T2S, I can write P01 by P02 to the power gamma minus 1 by gamma, and T2S by T1 I can express in terms of P2 by P1. Therefore, T2 by T1 would be equal to P01 divided by P02 into P2 by P1 whole to the power gamma minus 1 by gamma. Now substituting this in the equations for eta d, that is diffuser efficiency, we can get the expression of diffuser efficiency in terms of pressure ratio as P2 by P1 to the power gamma minus 1 by gamma minus 1 divided by P01 divided by P02 into P2 by P1 to the power gamma minus 1 by gamma minus 1. So thus, this is a very important relation which gives the diffuser efficiency in terms of static pressure and total pressure ratio. I'll discuss another important section, that's compressor characteristics, surge and choking. The performance map of a centrifugal compressor has been presented here by this figure, where the overall pressure ratio against the change in non-dimensional mass flow rate, that is m dot root over T01 by P01, has been illustrated at different speed. That means have indicated here different red line as shown, which are the characteristics of the compressor at different speed or as speed changes. Thereby, the pressure ratio will change with change of mass flow rate as speed increases, and these are the characteristics for increasing speeds. Furthermore, the ISO efficiency line, which are indicated by blue, have also been superimposed here, along with the green line, which represents the maximum efficiency line. Furthermore, the surge line, which are plotted by dotted lines, and the choke line are also presented here. Thus, I have written here the characteristics curve of a centrifugal compressor illustrates the overall pressure rise and efficiency against the mass flow rate at different speeds. So this is the zone where the compressor will work safely without choking or without its being into the surge region. When it will be in the surge, as I have indicated earlier, the machine will be completely unstable and we should not operate the compressor in the surge region. With respect to the choking flow, let me illustrate here. I have written here as the flow is choked when the through flow velocity in the passage reaches the local speed of sound at some cross section. This means that no further increase in mass flow rate is possible by increasing the rotational speed, and this condition is termed as choked condition, or we may say the compressor has choked. Now, from the characteristics map, it is evident that at all speed, the range of mass flow over which the centrifugal compressor will operate before surging or choking is quite wide. Further, surge occurs at increasingly high mass flow rate as speed increases, while the maximum possible mass flow rate at any speed is usually set by the choking line. Thank you for listening.